Let's begin our discussion with binary numbers. What is bi within the word binary? Bi is associated with the number 2, and so binary number has two possibilities, 0 and 1. Now, when dealing with circuit, 0 corresponds to off state and 1 corresponds to on state. Now, off state would be considered to false and on state would be considered to true. We can also represent false as a 0 volt and true as 5 volt or maybe other than 0 volt.
Now,
What is logic gates? Logic gates are basic building block of any digital circuit. Obviously, logic gates are itself a digital circuit. Using this logic gate, we can realize any Boolean expression or we can design more complex digital circuit. It is an electronic circuit having one or more input and only one output, as I have drawn the diagram below. But it is not true always. A logic circuit may have more than one input and maybe more than one output also. The relationship between the input and output is based on a certain logic. Based on this, logic gates are named as NOT gate, AND gate, OR gate, NAND gate, NOR gate, XOR gate, which is also called exclusive OR gate, and XNOR gate. So now NOT gate is represented with a symbol like tilde, slash, or a bar sign. AND gate is represented by a single dot. OR gate is represented as plus. NAND and NOR does not have any specific symbol because NAND is a combination of AND and NOT. NOR is a combination of OR and NOT. And the two more gates, XOR, whose symbol is a plus within a circle, and XNOR is represented as a dot within a circle. Or you can realize any Boolean function with these 7 gates. Now, the first 3 gates, NOT, AND, and OR, are called basic gates. Why? Because using these 3 gates only, you can design any digital circuit or you can realize any Boolean functions. The next 2 gates, NAND and NOR, are called universal gate. Using these 2 gates, you can also design any digital circuit or you can realize any Boolean function. Apart from this, you can also design the basic gates also. So why these are called, these 2 NAND gate, NAND and NOR, are called universal gate? We will prove it in my later videos. And the last 2 gates are called the special gates, XOR gate and the XNOR gate. Now let us check one by one. What are the operations and its working? We will not go into the details of each and every gate. For the timing diagram, internal circuitry or the discrete component used within these gates are to be discussed in my later videos. So in this video, I will discuss only the basic operations, its truth table, and the circuit diagram only. Now let us look at the NOT gate first. NOT gate has a single input and a single output, which I have represented as A and A bar. Why I have written A bar in the output? Look, so if you give 0 as an input to the NOT gate, you will get 1 as output. And if you give 1 as an input, you will get 0 as an output. That's mean 0 and 1 are getting inverted. 0 becomes 1 and 1 becomes 0. So this NOT gate is also called inverter. Now this is the logic diagram of the NOT gate, a triangle and a circle in front of it. If the input is 0, you will get 1 as output. And if you give 1 in the input, you will get 0 in the output. You can also think this NOT gate operation in your circuit diagram. Let us assume that when A is in an open state, we will say that it is in 0 state. If the switch is in closed state, that's mean we will say it is in the 1 state. So this light is our output. If it is glow, then it is in 1 state, and if it is not glowing, then it is in the 0 state. So now if the switch is open, the current will flow through the light and the light will glow. That's mean when A is in the open state, that means when A is 0, look at the truth table, when A is 0, then the light is in the on state, that is, it is in the 1 state, as I have written in the truth table. Now, if the switch is in the closed state, that is, if it is in the 1 state, then the current will follow the short circuit and the current will not pass through the light, and the light will remain in the off state. That's mean it is in the 0 state. The AND gate. AND gate has two input, A and B. So what are the different combinations for input? Since there are two possibilities, 0 and 1, so both AB can be 0, 0. A is 0, B is 1. The third combination is A is 1 and B is 0. And the last combination is both AB are 1. Now look at the output. If any one of the input is logic 0, then the output will be logic 0. So for the first combinations of input, both A and B are 0. So you are getting 0 as an output. In the second combination, A is 0 and B is 1. That's mean A, since A is 0, so you will get 0. In the third case, A is 1, B is 0. Since B is 0, you are getting 0 in the output. And for the last combination of input, both A and B are 1. So you are getting 1 in the output. That's mean if any one of the input A or B is 0, the output will be 0. So this is your logic diagram. It's a half circle or a D. It has a two input A and B, and the output will be represented as A dot B. And what will be its circuit diagram? Very easy. If you attach two switch in a series in the circuit, so what will happen? If any one of the switch is in the open state, if any one of the switch is in open state, that's mean 0 state, the light will not glow. When both the switches are in closed state, that is the last combination of the truth table, when both are 1, that is when both ABR is in the closed state, at that point of time the light will glow. That's mean the output will be logic 1. Then OR gate. So this is the truth table of OR gate. It has also two input and the same combinations 0, 0, 0, 1, 1, 0 and 1, 1. And what is the output? If any one of the input is logic 1, then the output will be logic 1. Look, for the first combination of input, both are 0, so you are getting 0. But in rest of the cases, either A or B or both AB are a logic 1, so you are getting 1 in the output. So if any one of the input becomes 1, you will get 1 in the output. And in the output I have written A or B, or is represented as plus sign. So this is the logic diagram. It is somehow look like the front portion of a fish. Okay. So it has also two input A and B, and it is producing A or B as an output. Circuit diagram where A and B are attached parallelly. So if any one of the input is closed, that is if any one of the switch A or B is in a closed state, that is in the one state, the current will flow through that switch and the light will glow and the light will be in one state. When both the switches are in open state, no current will flow through the light. At that time, the light will not glow. That means the output will be in the zero state. That is for the first combinations of input. Now come to the NAND gate. NAND gate is an inverter of AND gate. I have attached a bar over an AND gate. So it becomes the complement of AND gate. So if any one of the input is 0, the output becomes 1. And for the last condition where both are 1, it becomes 0. So this is the logic diagram of NAND gate. It has two input A and B, and the inverting operation, or you can say the NOT operation, is represented by a circle in front of AND gate. First it will do the AND operation and then it will complement the result. Now this is the circuit diagram of NAND gate, where AB are in series and both of them are attached parallel with the source and the load also. So what is happening here? Look at the last combination of input. When both the switches are in closed state, current will follow the short circuit and the current will not pass through the load, that is through the light, and the light will be in the off state 0. And for any other combination shown above,
current will pass through the light.
we can also realize this NAND gate with basic gates also. So as I've already said that it is a combination of AND and NOT. So you can do the AND operation by using an AND gate which will produce A dot B, and attach a NOT gate in front of it. So it will invert the result or complement the result to A dot B bar. So this diagram is equivalent to the diagram shown below. So if you are told to draw the NAND gate by using basic gates only, you can draw the above diagram. Now the next universal gate is the NOR gate. So this is the truth table of the NOR gate. You have already noticed that it is just an invert of OR gate. That's mean OR gate operation is getting inverted. What we have seen earlier, that in case of OR gate, if any one of the input is 1, the output becomes 1. But now it is just reverse of the OR gate. If any one of the input is 1, the output is 0. For the first combination of input where both A and B are 0, only then only we are getting 1 as output. So this is the logic diagram. Draw the logic diagram of OR and attach a circle in front of it. It has also two input A and B, and it will produce A plus B bar. And the parallel combination of A and B is attached parallelly with the load and the source also. So what is happening here? When both the switches are in the open state, then only the current will flow through the light only and the light will glow. That means the light is in the one state. For the rest of the combination of input, if either A or B, if any one of the switches is in the closed state, the current will follow the short circuit and the light will not glow. So the light will be remain in the zero state. Now, you can also realize this NOR gate with the basic gates. Let's draw the OR gate circuit first, which will produce A or B, and attach a NOT gate, that is an inverter gate. In front of it, you will get A plus B bar. And this diagram is equivalent to the diagram shown below. Now come to the special gate, XOR gate. It is also called exclusive OR gate. It gives a true output when the number of true input is odd. Read this line very carefully again. It gives a true output. That means it will give you a output 1 when the number of true inputs, that means when the number of 1 in the input is odd. So you have to count the number of 1 in the input. Look, in the first case, both are 0. So there is no question of 1. So write 0 in the output. In the second condition, A is 0 and B is 1. So how many 1 are there? Odd number of 1 is there. So the output is 1. In the third case also, there is an odd number of 1. There is a single 1 over here. So you will get 1 in the output. Look at the last combination of input. Both are 1. That means there are even number of 1. That's why you will get 0 in the output. In some cases, it is also said that when both the inputs are equal, that is in the first case and in the last case, the output will become 0, and when the inputs are dissimilar, that is in the second and the third combination of input, it will give you a 1 output. But this is not true for 3 input, 4 input, or more than 2 input XOR gate. So keep it in your mind. It gives a true output when the number of true inputs is odd. So if you count odd number of 1 in the input, then only you will write 1 in the output. Now, what will be the logic diagram of this XOR gate? So it has 2 input A and B, and the output is represented as A, a plus within a circle. This is a symbol of XOR gate, then B. So if you are told to realize this XOR gate with the basic gates only, so how you will do? Realizing XOR gate with basic gates. So what is the truth table of the XOR gate? So for the 2 input XOR gate, the first combination and the last combination are producing 0 in the output, and the second and third combination of input are producing 1 in the output. That is, odd number of 1 in the input are generating 1 in the output. Now you will consider the high output only. I mean, which has logic 1 in the output, you will consider that row only. Here, A is 0 and B is 1. Before realizing XOR gate with basic gates, first of all, you have to derive an expression or a Boolean function. By using that Boolean function or expression, we will draw the XOR gate with the basic gates only. So first check how to derive the expression. So you have to write like this: A XOR B equal to A bar dot B. Why I have written A bar dot B? Since A is 0, so 0 is represented by the invert of A. So when you are getting 0, just complement that variable and write down. So A bar. And what is the state of B? It is in the 1 state. So just simply write down the variable. And since both are occurring at the same time, when A is 0 and B is 1, that's why I have written dot, that is AND. So A bar dot B. Now there is another condition where you are getting output 1. So the third combination of input. Here A is 1 and B is 0. So since there is another condition, so just write down or A dot B bar. Since A is 1, that's why I have written A, and since B is 0, so write down B bar. Since we are expressing 0 as the invert of B, so the whole expression becomes A bar dot B or A dot B bar. You can also say A bar B plus A B bar. So this is my expression. Now, how to draw this expression with the basic gates? Look, the expression contains only basic gates, not and, or, and, not. Draw the line of A and draw a connection from here and attach a inverter or a NOT gate, and this line will be treated as A bar. Similarly, draw another line B and it has a B bar line. So first of all, you have to draw the A line, A bar line, B line and B bar line. Look at the A bar B. That's mean you have to draw the connection from A bar line and B line. So this is the connection from A bar line and this is from B line. And what is happening with them? And AND operation. Dot means AND operation. So just draw an AND gate. Similarly, the second half of the expression, which has A dot B bar. So that's mean you have to draw the connection from A and B bar line. So I am drawing a connection from A line and from the B bar line, and AND operation is there within A and B bar. So draw a AND gate. Again, the output of this two AND gate will be inserted to an OR gate. Then you will get the final output A bar B or A B bar, which is equivalent to XOR gate. XNOR gate, but a complement of XOR gate. So in case of XOR gate, if the odd number of inputs are 1, the output is 1. It is just opposite of XOR gate. The output of the XNOR gate is the logical complement of the exclusive OR gate. That's mean if there are odd number of 1 in the input, you will get 0. And for 0 0 combination and 1 1 combination, you will get 1. And this is the logic diagram of XNOR gate. Just draw the XOR gate and attach a circle in front of it. So you will get A XNOR B, where XNOR is represented by a dot within a circle. This gate can also be realized with basic gates only. Check. So this is the logic gate. So this is the truth table of XNOR gate. Again, we have to consider the high output. That is the first one where both A and B are 0. So write the expression first. A XNOR B equal to A bar dot B bar, because both A and B are 0. 0 is represented by the bar of that variable, and since both are occurring at the same time, so AND. There is another situation for an high output, that is the last combination where both A and B are 1. So what you have to write? The OR sign and A dot B, because both A B are 1. And this will be the logic diagram of XNOR gate. As before, draw the line of A, the line of A naught, B, and the line of B naught. From the first term, what we are getting, A bar and B bar. So draw the connection from A bar. This is the line of A bar and this is B bar. And a AND operation is operated in between them. So just draw a AND gate. Similarly, there are A dot B. Draw a connection from A and B line and draw AND gate because AND is in between A and B. Again, their output will be inserted to an OR gate because these two terms are attached with a OR gate. Just draw the OR gate and you will get the final output A bar B bar plus AB, which is equivalent to A XOR B. If you have any more query regarding this topic, you can reply me back, write in the comment box, or you can also send me email, which is provided or given in the video also. Subscribe to my channel Online Technical Mentor and press the bell icon for latest update. Thank you.